So this is lesson 20.2.7, friction and inclined planes, and we will be doing a lab on this as well. The lab we usually do is kind of a group lab where I have it set up here and we do some measurements. We'll probably be doing something with it late next week. Determine the normal force and the force due to friction for a mass on an inclined plane. 2 classes ago we did that for a horizontal surface. To begin with, sketch a diagram showing a 12 kilogram mass at rest on an inclined plane when the angle is at 30 degrees. And then you're told something, and I'm going to hand out rulers so that we can, we're human beings, we're not chimpanzees, we can draw a nice diagram. We tend to always draw the object as being like a block of wood or a rectangle of some kind. Whatever you draw for the object, it has to have a flat surface making contact with the ramp. So what we have is an inclined plane. You can estimate what 30 degrees is. You don't need to get a protractor. I would say that's about 30 degrees. Whether you want to complete this diagram by making a triangle out of it, by dropping this down or not, is entirely up to you. It doesn't matter. But this is a 30-degree angle. And then we have an object on it. It's on an inclined plane. So it's making a nice, clean contact surface to surface. It's at rest. Now, why is it at rest? Well, it turns out it doesn't matter why it's at rest. Maybe it's at rest because friction is great enough to suspend it there. You understand, of course, if I put an object on an inclined plane, that the greater the angle becomes, the more likely it is the object will start slipping off. And that tells us something, maybe important, that the greater the angle, the less friction there is. Maybe that's a hypothesis we could test out. The force of friction has to depend on the angle in some way. So there is the diagram. If you want, you can put the mass on there. I don't think it really matters. I'm going to go ahead and put it on there, 12 kilograms. Anything else we can label? Well, the coefficient of friction is 0.75. We can just put that off on the side here. Mu equals 0.75. Anyway, there's our diagram. That diagram wasn't given to you, was it? No, I'm looking at yours. Yours is like it's print perfect. So now, number 2 asks us to sketch, and I'm going to go back and draw it on here. Asks us to sketch a free body diagram. But now just look up here. Just look up here. Don't write anything, don't draw anything. If I said draw a free body diagram, the fact of the matter is, if it's just sitting there, we're not touching it, okay? You're not drawing this. The free body diagram would include a force of gravity. You're not drawing this. This is the force of gravity. And it would include a force of friction, right? Except that since it's on an inclined plane, this force of gravity vector is not helpful in analyzing what happens. I want you to understand before we continue that this force of gravity is doing 2 things to the block of wood. It is pushing it against the ramp, and it is pulling it along the ramp. This force of gravity, and I'm going to make my force of friction longer. It doesn't really matter because you're not drawing this, okay? This is learning that's going on in your brain. This force of gravity is actually pulling this box against the ramp and pulling it along the ramp. Would you agree? Okay. Those 2 gray vectors add to give the force of gravity. Those 2 gray vectors are components of the force of gravity. Normally, when we worked with components of forces, we talked about left, right, and up, down, correct? Well, that's because the objects were very sensibly oriented on a horizontal surface. We talked about forces left and right because that's the direction the object on a floor could move. We talked about up and down because that led us to the normal force. Well, here, since the ramp is like that, we have to talk about forces in this direction, towards the top of the ramp and the bottom of the ramp, and perpendicular to the ramp. So that's what we are asked to draw a free body diagram for. It says, draw a free body diagram, and this is where I stopped, and now I'm going to say, showing the forces that act parallel to the plane and the forces that act perpendicular to the plane. So, is the force of friction a force that acts parallel to the plane? Yes. Now what we need to do is calculate the component of gravity that is acting parallel to the plane and perpendicular to the plane. And I'm going to go through this explanation once, and then I'm going to give you formulas that would be given to you on an exam. If you have a ramp, and this is theta, I don't want it that steep. And this is theta, and you have your mass on the ramp. So again, I'm going through this once. And then I will give you formulas. But I would like to go through it because I think in post-secondary you would be given the formulas. Okay? This force of gravity is the real force acting on that. Okay? But that force of gravity is doing two things. It is pulling the object against the ramp. The gray vector that's longer is the vector that's pushing the box against the ramp, and the gray vector that's shorter is pushing the box along the ramp. This is called the force of gravity parallel to the ramp. This is called the force of gravity perpendicular to the ramp. Are you with me here? It turns out, due to geometry, that this is the same angle as theta of the ramp. I think you can kind of see we're talking about similar triangles. I don't want to get into a geometry lesson. But that is the angle. This is the actual force of gravity, correct? So if I asked you to find the parallel component of gravity, you'd use trigonometry. You would say sine of theta equals the opposite side over the hypotenuse. Which means the parallel component of gravity will be the regular force of gravity, will be the magnitude of the true force of gravity times the sine of the angle. And we're going to use those in a second, but I want to show them to you first. And if you do the same thing with cosine of theta, you'll have cos of theta equals fg. Well, that's adjacent, which is the perpendicular component over the force of gravity, which means that the perpendicular component is the force of gravity times the cosine of theta. And somewhere along the way, we're going to be calculating these forces. Why don't we calculate them now? And the reason why I'm going to want us to calculate them now is our free body diagram should be drawn fairly well. Okay? So, just somewhere on here, and if you take a look at your handout, I'll show you this. If you take a look at your handout, it says determine the normal force. It says determine the magnitude of the force of friction. And I also want us to determine the force acting parallel to the ramp. Well, we want to find the values of all of the forces, okay? So let's just do that here. Let's go Fg parallel equals the force of gravity, which is mg times sine of 30 degrees. That's what I just taught you. The parallel component is the one that uses sine. So take a minute and calculate what that force is. Very close to 60. 58.86. I'm going to call it 59. This example is a learning example, okay? 59 newtons. Oops. So the reason why I say it's a learning example, I don't care about precise values here. It's about 59 newtons. That is going to be the force, and don't draw it yet. After I printed out this lesson, I kind of thought, I should have approached it in a different way. Let's do all the calculations first, then we'll draw the result, okay? That is a force that's down the ramp, right? That's a force that's going to be drawn in a bit here, okay? I don't want you to draw it yet. We don't need to. Let's calculate now the perpendicular component. That's going to be mg, so it's going to be 12 kilograms times 9.81 times cosine of 30 degrees. It's very close to 100 newtons. I'm just doing a rough estimate in my head. What do you get, Maxime? 101.9, so let's call it 102 newtons. Okay. And I want to point something out to you that I hope is obvious when it's put into words, but maybe not. Since this angle is less than 45 degrees, we would expect the brunt of gravity to be pushing against the ramp rather than down the ramp. At higher angles, if you take a look at my arm, when I get to an angle of like 70 degrees, very little of gravity will be pushing against the ramp. Most of it will be going along the ramp. Make sure your calculator, of course, is in degrees. So we're all able to get that? Okay. Let's draw those. I've asked you not to draw any forces, so let's leave the force of friction out of it for now. Let's draw those. Like the force of gravity perpendicular to the ramp is, it's not twice as great, but it's getting to be close to twice as great. So if I draw this, and I'm just drawing it this way so that I can get my angle right, and I say that that is the force of gravity, I'll go a little bit longer. I say that that is the force of gravity perpendicular to the ramp. We can label that. So now you're actually populating this diagram with vectors and labels. That's the force of gravity perpendicular to the ramp. Then the force of gravity parallel to the ramp is a little bit more than half of that. Right? This is 101 newtons, and this is only 60 newtons. Well, 59. So we can label that. And again, I apologize. I don't think I've organized this whole warm-up in a really efficient way. Okay? So we have those two forces. Are there other forces? Who can tell me one other force that is acting on this object at this point in time? Ephraim? And the normal force has what value? We know the value of the normal force. It's 101 newtons. Because the normal force is the force pushing the box perpendicular to the ramp. There's no acceleration along that dimension towards the ramp or away from the ramp. So the normal force is balanced. The normal force is balanced by the component of gravity that is perpendicular to the surface. Those two forces are equal. I want to just back up now, and everybody take a look at this. What is the normal force equal to here? Well, it's equal to all of gravity, right? Okay. What is the perpendicular component to the surface of gravity? The whole thing. In fact, do you agree that the angle is 0 degrees? The perpendicular component of gravity will be mg sine, cosine of theta. That's what we've taught. And this is a formula I'm going to give you. Go ahead and take, I don't care, 10 kilograms times 9.81 newtons per kilogram. Just do that. Just take 10 kilograms times 9.81 newtons per kilogram. My goodness sake, do we need a calculator for that? It's 98.1. Multiply that by cosine of 0. Get 98.1. This statement that we've stumbled upon for an inclined plane, that the normal force has the same magnitude as the perpendicular component of gravity, is true all the time. The normal force will always be mg cosine theta. It's just that on a horizontal surface, cosine of theta is cosine of 0, which happens to be 1. Okay? All right. Now, this is getting somewhere now. Somewhere along here you were asked, we're getting to this conclusion to this. What is the normal force? We've determined that. The normal force has a value of 101 newtons because the normal force is equal in magnitude to the perpendicular component of gravity. And we've already calculated the perpendicular component of gravity. So we know the answer to this question. These are not the same force, they're the same magnitudes because they balance in that dimension. What's the magnitude of the force of friction? We can do this. Because the force of friction is mu Fn. And this is Fg perpendicular. Why is Fn, Fg perpendicular in magnitude? Look at your free body diagram. Those two forces that I'm indicating with my arms are balanced. And we already calculated that. We calculated this to be 101 newtons, which means this is 101 newtons. I can't remember, was it 0.75 from mu? So this will be 0.75 times 100 newtons, 101 newtons. I'm actually going to use more decimals here. This was that force, right? Okay, so times 0.75, about 76 newtons. And now we come to the point where it should all start coming together in your head. That force of friction is 76 newtons. Will this box accelerate down the ramp? There's a force pulling it down the ramp, right? Why is this force not sufficient to pull the box down the ramp? Because it's only 59 newtons. And the force of friction is 76. So when we draw this, and here's where we run into a problem, but you're just going to have to cope with it. I'll put some numbers on here. This is 59 newtons. This was 101 newtons. Yes? This is 101 newtons. And this is 76 newtons. It's the force due to friction. The problem is this. Well, the question I'm asking is this. What's the net force acting on the box? It's 0. It doesn't accelerate. Just because the force of friction up is more than the force of gravity parallel down doesn't mean the box, you put it on there and all of a sudden the box starts going up the ramp. That would be a weird world to live in. So we would still say the forces are balanced here. It's like you pulling that apparatus across the countertop yesterday. Maybe the force of friction is 6 newtons and you're pulling with 4 newtons. Does that mean that the net force is 2 newtons in the other direction? No, the net force is still 0. The application of the physics doesn't happen until the motion starts to happen. Now, if we would have gotten 26 newtons for the force of friction, then we could find the net force and find the acceleration. But that diagram says it all. So we've drawn the free body diagram, we've calculated that, we've calculated the magnitude of the force of friction, and if you turn to the next page, we're going to do 2 examples, and then you're going to have 3 problems to do for tomorrow, and then you can use the rest of the class to work on your lab report. I will give you these formulas for exams. Okay, they're not on your formula sheet. If I don't give them to you, I don't really know what I'm testing. I'm testing your memory if I don't give them to you. I want you to be able to understand that on this diagram here, this is the force of gravity perpendicular to the ramp. This is the force of gravity parallel to the ramp. Now I want to just briefly explain why we spent all this time learning that. It's because to analyze the motion of objects on a plane, you need to determine the force of friction, right? Well, the force of friction, yesterday, and every day before yesterday when we learned friction, you would have said it's mu. You could have taken a shortcut and said mu mg, correct? Because on a horizontal surface, I don't want vector symbols there. On a horizontal surface, this is the true formula, and on a horizontal surface, Fn is mg. Is Fn mg for this diagram? No. It's the parallel, it's the perpendicular component of gravity. Right? This force here is always going to be balanced with the normal force in the opposite direction. So this is where you start with the force of friction. You start right here. And then you say, okay, how can I find the normal force? In this case, it's the force of gravity perpendicular to the ramp, which, if you're really following, is always the case even if the ramp is not a ramp. Okay, let's try this now. A 12 kilogram mass is on an inclined plane that makes an angle of 64 degrees to the horizontal, and you're given the coefficient of friction. What's the force due to friction? Well, the force due to friction is mu Fn, but Fn is the same in magnitude as Fg perpendicular. I feel as though I can't say that enough. The magnitude. It's not that they're the same force. They are not the same force. They have the same magnitude. So if you look up here, please, and I know that many of you are eager to just get to the answer. You know how to do it. But if you look up here, I suppose what you could do is go Fg cos theta, and then go mg cos theta, and actually calculate this number and get a number, and put the number, whatever you get, in here. Capiche? I want you to get in the habit of doing the opposite. Well, not the opposite. Of doing this instead. Of building a single equation. There are going to be problems in physics in this course that cannot be solved in steps. You have to build a single equation. So what I'm doing is I'm changing the Fn to Fg perpendicular. Why is that true? Man, I don't want to draw this diagram every time. It's true because the ramp makes it true. The ramp prevents any motion against it or perpendicular to it in any way. So those two forces must balance. So I'm not going to draw this every time. I'm just going to say that that's the case. And then this becomes Ff equals mu times mg, which is the force of gravity. I'll do it in steps. Fg cos theta. And then Fg is found by taking m times g. Mu mg cos theta. And by building a single expression, it's just a matter now of putting the numbers in your calculator. I mean, I'll write them down, but. So this will be 0.62 times, I'm pretty sure I still saw 12 kilograms, times cosine of, I think I saw 64 degrees. And I forgot my 9.81. That would have been embarrassing. Newtons per kilogram times the cosine of 64%. And you know, once you build this equation, as soon as we get to, say, here, everyone, the physics is done. We're done the physics. Now we're just putting stuff in from a data sheet and numbers from the question. Ephraim, do you have a question with that?
The last Fg, is that supposed to be friction? Or is that?
This here?
No, below that. And left.
This?
So you got Fg equals.
Oh,
That,
yeah. Without a doubt. Thank you. Too many forces flying around my brain. Yeah. It's definitely the force of friction. So we can run that through the calculator. Thank you for that, Ephraim. 0.62 times 12 times 9.81 times cosine of 64 degrees. Those numbers were correct, though, weren't they? Okay. So I'm getting 32 newtons. That's the answer to the question. By the way, we're done this question, okay? By the way, if I ask you to find the parallel component of gravity, which doesn't determine what the force of friction is, but if I ask you to find the parallel component of gravity, it would be 12 times 9.81 times sine of 64, right? The parallel component of gravity is 105 newtons. Will this box accelerate down the ramp? Yes, because that's more than the force of friction. And the net force would be this number minus that 32 newtons. And then you could divide that by the mass because F net equals ma. That's where we're going. And it will be more complicated than that because I might give you a situation where this is what's going on and somebody is pushing the box up the ramp with 20 newtons. The box is still going to accelerate down because you have this 105 newtons pulling it down the ramp. You have me fighting with 20 newtons to try to prevent that from happening, and friction helping me out with 32 newtons. That's still not enough. The box and me are going to go tumbling down the ramp. Let's try one more. A 6 kilogram ramp. A 6 kilogram mass is on an inclined plane that makes an angle of 38 degrees to the horizontal. The force of friction is 20 newtons. What's the coefficient of friction? Well, the coefficient of friction is the force of friction over the normal force. But the magnitude of the normal force, I'll be fancy this time and put all my symbols and stuff on there, is the same as the magnitude of the force of gravity perpendicular to the ramp. And this is m. I always skip that step. I'll write them both down. This is the force of gravity times the cosine of theta, which is mg cos theta. How many of you would be fine in me saying FG perpendicular is this without writing the force of gravity times cos of theta? You know, on the formula I give you, it's going to say FG cos theta, but I typically will just go m times g times cos of theta, because FG is mg. The force, when I say FG, I just want to make abundantly clear here. When I say F times G or FG, that G is a subscript, right? It's not 9.81. It's just a subscript to the force. So that should be pretty easy. Mu equals the force of friction over mg cos theta. Again, you can calculate this first as a number and then put it in, or you can do what I've done. I have to take a quick peek at these numbers. Is this the question you have? I didn't think so. Oh, that's the assignment. There we go. 38, 20 newtons, 6 kilograms. 20 newtons divided by 6 kilograms times 9.81 newtons per kilogram times cosine of 38 degrees. You know, the only thing you have to be careful of here is if you're going to enter this into your calculator in one fell swoop, when you go divided by, you have to have that in brackets. When I enter it, I go 20 divided by 6 divided by 9.81 divided by cos of 38. How many of you have picked up this habit of mine and do that? It's just a simple thing. It's divided by, I don't know, you could argue it's probably more keystrokes. I get 0.43. Anybody else get that number? Perfect. So the coefficient of friction here, mu, is 0.43, and we're done. You only have a few problems to do for homework, those ones attached. I was going to maybe come up with some more, but you have that lab report to polish up. And if you get done early today, we don't often get done early, so if you get done early, that's fine.